Thermocouple is an industrial-grade temperature sensor. It's available in various connector types for various applications, and it's very rugged temperature sensor. It's used in harsh environments, extreme temperatures. The operating temperature range is also very wide, from minus 270 degrees to up to 3,000 degrees, and some thermocouples can go even higher than 3,000 degrees. But for most common industry applications, thermocouples are available up to 3,000 degrees. So a typical application for these types of thermocouples are really industrial application. You see them in industrial ovens, boilers, furnace. We're talking about large furnace. And on 3D printers as well, the extruders are maintained with a thermocouple for a high-end 3D printers to see those. Kilns, smelters, all of those use thermocouples. Like at higher temperature, usually that's either that or a resistive temperature detector or RTDs are used, but RTD has a temperature limit of about 600 degrees, and anything above 600 degrees, thermocouples are utilized. In the automotive industry, thermocouples being utilized in engines, exhaust systems, motors, gigantic, huge motors for industrial applications or automotive aerospace applications. Also in the petrochemical industry, because of the rugged nature of this temperature sensor, it withstands harsh chemicals very well, or high pressure application or high vibration applications as well. For consumer application, you see them in refrigerators, freezers as well, and water heaters as well. So if the 40-gallon water heater you have at home, it's got a nice long thermocouple in there, measures the water heater temperature. Thermocouples are used for food pros for their fast thermal response characteristics. Those are the typical applications for a thermocouple.
Okay, that totally makes sense. But Azana, how exactly do these work?
Thermocouples are really unique temperature sensing devices. The key element about the thermocouple is that there are two dissimilar wires, metal alloys, for example, chromel and alumel, iron and constantan, chromel and constantan, some combination of these various alloys. When you join them, when you have a point of contact for the two wires and heat is applied, what happens is the electrical characteristics of the resistive element and excited electrons generates voltage. And that voltage can be measured at the opposite end, on the open wire end. And those two points are called hot junction and cold junction points. The point of contact for the two wires is the point where the thermocouple is placed into the harsh environment or high temperature environment, whereas the cold junction is the junction where the measurement is being conducted, and that is usually at room temperature. And basically, the sum of the temperature at cold junction and the hot junction gives you an absolute temperature reading. The voltage that's measured is called the Seebeck effect or electromotive force. As you can see, thermocouples don't need any excitation, current or voltage or supply or anything like that. They are self-contained and they may generate the voltage proportional to changes in temperature. So that's how they operate.
Okay, so what kind of solutions would you suggest in this space? Now, I would imagine that I have a lot of options, especially when it comes to the materials themselves.
Yeah, thermocouples are available in various types. There are several materials depending on the temperature range and linear characteristics that the application requires. So in this case, I have a table on the right side of the presentation. And as you can see on the table, the most common thermocouples as top three are type T, J, and K. Those are just typical names used to identify these different types of thermocouples. And the rest of them are somewhat specialty. And you can see the temperature range and it's how wide the ranges are for each thermocouples. And they provide different, like I said, linear characteristics for the sweet spots of sensitivity. And the key thing to look at is on the right side of the table, there's a voltage range. And as you can see, the EMF or electromotive force or the Seebeck effect is measured in the units of millivolt. For type D thermocouple, minus 6 to 20 millivolt is the range. That's very, very small. Type K goes from minus 6 to 54 millivolt. And so as you can see, you can go on, and you can notice that the voltage range is very, very small. So if you need a 1-degree resolution, that would be very difficult to achieve. So there's a compromise between sensitivity or range and resolution. in the application. But when you're considering a thermocouple solution, clearly the first thing that comes is analog instrumentation. And with the high gain, typically instrumentation amplifiers are used, and that's the right way to go for a lot of applications. But say you have a gain of 100, then the range is going to be limited. And so you have to compromise between the range and the resolution you need for the temperature. Some applications use precision delta sigma ADCs, high resolution delta sigma ADCs, and those are very useful. They can be costly in some cases. You'll need low tolerance resistors and capacitors. And scaling and error nailing is also necessary circuit requirement. And temperature calibration is also needed. Obviously, you need to know where your reference temperature is and calibrate your circuit to that. And another key element, as I mentioned in the previous slide, is knowing what your cold junction temperature is, because that is your reference temperature to accurately know what the absolute temperature is. All of these are components needed to build a thermocouple electronic solution.
So say I decide on a thermocouple solution for my next design. Azana, what kind of circuits should I consider?
There are several solutions, but the most typical solution, as I mentioned in the previous slide, is instrumentation amplifiers. But you'd have to consider the cost of the instrumentation amplifier as well as the integrated A to D converter. You would have to digitize your signal accordingly for data logging purposes or to turn on a switch, whatever the application requires, right? And a cold junction compensation temperature sensor is also needed. So if you look at the bottom slide, you have the thermocouple in one end on the left side of the slide, right, with the extreme temperature. It's signified by a red mark, and you have the cold junction. On the bottom side, you have the temperature sensor, a little yellow dot. That measures your overall ambient temperature at the cold junction. And on the right side, you have the instrumentation amplifier, and you do have a trim gain or a gain adjustment network. So these are really the basic building blocks for thermocouples. In both cases, for the temperature sensor, you have voltage output, and for the thermocouple, there's a voltage output as well. So in a digital domain, you can do the summing and calculation and linearization. Now, as you look at the circuit, the key things one would have to consider when building a thermocouple solution, precision instrumentation, is high impedance input. Also, low noise is required, low offset voltage, and low gain nonlinearity was also a must. Microchip, we have several analog solutions for digitizing a thermocouple. I suggest visiting microchip.com/analog for a list of components that one could use